All right, let's continue on with what we're doing. We want to integrate over the region bounded by y equals x squared for f of x, y equals the square root of x over y. I think this might be easier to work with later on if we write it as x to the 1/2 over y to the 1/2, or x to the 1/2, y to the negative 1/2. That'll be easier to work with later. We are going to need to know where these two functions meet no matter what. So where do these meet? Let's find out. X equals y, and it also equals x squared. So we can eliminate the middleman. Do not divide by x. I know you learned to do that shit, but it's wrong. And while it does not change the answer that we're looking for here, if you had divided by x, you still would have gotten the answer we wanted. It actually eliminates the other answer, which is we already know. The 0, 0 is obvious, but it's bad practice to get in the habit of doing shit you can't.
Squares, there should be two solutions.
Exactly. So we can see x equals 0 and x equals 1. And we clearly knew one of them. It's the origin. This one has got to be there, and we can find the y value by y equals x, which equals 1, which gives us the 0.11. And we haven't even talked about integrating yet. But we needed that no matter which setup we used, so it was worth talking about now. I'm going to throw some extra points down now that I know where they are. This is a 1, and that's a 1. Now we can do this two ways. We can do dy or dx as our primary thing, which means integrating like that, where dx is the outer integral. And if we set it up that way, dx being the outer integral would go from 0 to 1, and then we got the dx. The inner integral, we got to do, what is y doing? Y is the lower limit, or the lesser boundary is x squared, and the greater boundary is x. I'm going to use the word greater and lesser rather than upper and lower, because if you go left to right, upper and lower is meaningless. But greater means moving further to the right. And that would give us the dy on the inside, and then we still have f of xy. And we can take a look at the other setup. If we do the other setup, 0 to 1 is the dy. And in this approach, we're going that direction. So we need x in terms of y. So the lesser line is y equals x, so we could put y there. But the upper line, the greater line, is y equals x squared. And if I want it in terms of x, I take the square root. Technically, I have plus or minus the square root of y, but we're definitely on the side where it's positive. So that's definitely would be the square root of y there. And we could do that. And I don't know about you guys, but if I can avoid having square roots in my limits of integration, that sounds fucking joyous. So I say, let's go with this choice. Shit will be easier. And I think it's when you're setting it up, I think it's actually handy to write f of xy or f of xyz first, then replace it. That way, like, you don't get confused by what the fuck's going on the inside. Because when we get to 3D, which is in a few chapters, like when we have triple integrals, not chapters, but a few sections. Then we're going to look at doing it in cylindrical and spherical, and like which coordinate system is like, if you just write f of x, y, z, each of the other systems has a different component going in. Like cylindrical and spherical have more than just d rho, d phi, d theta. For spherical, there's more to that component, which you'll see when we get there. And knowing what comes from f of x, y, z, and what comes from being in the coordinate system is worth distinguishing and knowing ahead of time. That way you don't confuse yourself. We're going to lock in that one. We're going to do this one. So let's replace that f of x, y with what it is. That is x to the 1/2, y to the negative 1/2. And we're doing dy and dx. Now we're integrating inner function first. So this is the part that's important right now. In fact, even though you don't need to, you can, if it helps with the integration, rewrite it like this. 0 to 1 x, x to the 1/2. Then do this y, x squared x, y to the negative 1/2 dy. Then have our dx. Like this is nestled inside the other one. They are multiplied together, so we can do that. I don't know that it's really helpful, other than maybe so you don't forget the fucking x to the 1/2 when you integrate, like I tried to do this morning. So when we integrate this portion, it goes up a power, and then we divide by the power, which gives us a 2 root y. And we still have the x to the 1/2 out front. I've got 0 to 1, 2 to the 2x to the 1/2, y to the 1/2, and we're evaluating y to the 1/2 from y equals x squared to y equals x, and we got our dx. Okay, so I got 0 to 1, 2x to the 1/2, and then we do the distributing that. I got y to the 1/2, so I got square root of x, or x to the 1/2, minus x squared to the 1/2, which will just be x. Right. And we got our dx, and we want to distribute that first x to the 1/2. We want to clean this up before we try to integrate. This ends up being 2x. Let's put the 2 out front so that we don't forget that it goes on both. And then x to the 1/2 times x is x to the 3/2. All right. X to the 5/2 divide by that means multiply by the reciprocal. And we're going from 0 to 1. Plugging in the 1 is nice, and plugging in 0 is nice. This gives us 2 times 1/2 minus 2/5. I actually think it's easier to distribute here and not find a common denominator. This becomes 1 minus 4/5. And that's easier to see that. That goes to 1/5 right away. You could have found a common denominator, then multiplied by 2, but boom, not too bad. It does help to stop and do this, like go, which path do I want? Unless you see the path you like right away. After a little while, it starts to become more of a second nature, like which way you want to integrate. You just got to remember how to set it up. People are still right, so I'm giving a little bit longer on this one. All right. I see pin still moving. Waiting. Not just your pin. Don't worry, Chris. All right. So here, find the volume of the solid in the first octant bounded by the paraboloid z equals x squared plus 3y squared. That's going to be my f of x, y. Below by z equals 0, and laterally by y equals x squared and y equals x. So while that's a shitty paraboloid, it is like a conic section going upward. And it says between that and z equals 0, that's the xy plane, which means it's below that. So this is designed to kind of like show that it's below. And if we graph that region in the xy plane, because that's what we're doing here, we see that we get the same shape we had last time. In fact, it's identical to the last problem. Y equals x and y equals x squared. So same boundary conditions as problem 2. Which means we can use either of the setups. In fact, the fact that we wrote f of x, y rather than putting it in right away, I'm going to go copy it. These two both work in this situation. Like we can do either of these right now. It's just a different f of x, y right now. And so because we're not psychopaths, you might be a psychopath. If you want to be a psychopath and use the y and square root of y, knock yourself out. I'm going to stick with the same route we went before. That gives us 0 to 1, x squared to x. F of x, y has changed to x squared plus 3y squared. Now, quick note, if your OCD is kicking in and you don't like x squared and x, remember you can change the limits of integration, swap them if you introduce a negative sign. Some people like having the x squared above the x, and it fucking drives them wonkers. Like this just fucking feels wrong. And it makes me twitch. In fact, you look at my fucking lecture notes from previous semester, I deliberately used the x squared on top and I used the negative sign. Like I wrote it on top and then I realized it wasn't right. And I had to add a negative sign later on. And it was when I found a fucking negative volume kind of thing. Uh, but like it was making me twitch. So if it makes you twitch, you're not alone. Again, not separable because we have limits of integration that have variables in it. So we just got to go through this slowly. We are integrating with respect to y. which means the x squared just gets a y on it. And 3y squared goes up to y cubed, and we divide by 3, we just get y cubed. And we're evaluating from y equals x squared to y equals x. I have x squared times x plus x cubed minus x squared times x squared plus x squared cubed. That's an x cubed, that's an x cubed, that's an x to the fourth, x to the sixth. Make sure we distribute the minus to both of them. We've got 1. We can put the x cubes together, but the other stuff doesn't combine. These parentheses are important. The dx is hitting all of them. So, like, don't be sloppy. Under threat of loss of points, don't be sloppy. Don't make me wave my big stick around. This should be straightforward, hopefully, at this point. We go up a power, divide by the power. Up a power, divide by the power. Up a power, divide by the power. That'll simplify to a 1/2 there. And we're going from 0 to 1. Hopefully you guys are comfortable with me jumping straight to this right here without having to show putting in the 1 and the 0. Get a common denominator. We got to multiply these all together, which would give us 70 on bottom. This needs a 7 times 5. This needs a 2 times 7. This needs a 2 times 5. I get 35 minus 14 minus 10 over 70 is 11 over 70. Okay. Next problem. The integral's already set up for us. That's nice. That's handy. Can I do anything with this? What's the integral of e to the x cubed? I don't know about you. I have no fucking idea. We get that's my inclination. Let's try u sub. If I do that, I get du equals 3x squared dx, or 1/3 du equals x squared dx. I do not have, there's no x squared here. which means U sub may not be helpful right now. So we could try to change stuff over, maybe try integration by parts, something like that. But like when you've got a multiple integral, the easiest thing to try is maybe swapping the order of integration first. So let's try swapping the order of integration. And the way we go about doing that is drawing a picture. Now remember, this is like the z equals f of x, y, and it's unrelated to boundaries. Unrelated to boundaries in x, y. So we don't need to look at the e to the x cubed while we're looking at the setup. Just the limits of integration. We want to use them both. Yeah, we're going to look at both. Because we're going to swap them. We need to know what both look like in the new system. Let's try order. What the fuck did I write? Let's try swapping the order of integration. So sketch it based off the limits of integration. And this might be helpful to write out what they are. So I'm going to use a highlighter to like connect dots here. This 0 to 4 is going with the dy. So it's a y thing. And the 2 root y is going with dx. Which means if we look at the y, 0, this is the y1. 0 is less than or equal to y is less than or equal to 4. And same setup, we're going to do square root of y is less than or equal to x, which is less than or equal to 2. So let's map that. I'm going to put in little like dashed lines to like indicate the boundaries we're looking at. I've got 0 and 4 right there. Y equals 0, y equals 4. X equals 2 is right here. And let's take a look at square root of y. To get the, yeah, to get the line, we actually don't need the inequality. And we can square it and we get y equals x squared. Which means we've got this right here. So now we're either in region A or region B. So which region are we in? Try a test point. If you're uncomfortable with what happens by squaring it and keeping the inequality, try a test point. Maybe let's try the 0.13. And maybe let's try 3 halves, 1 half. In this. So square root of, oh, back to the less than or equal part though. Square root of 3, is that less than or equal to 1? This is section A. Is that true? No. False. So it's not in A, which means it's in B, but if you want to confirm it's in B, is square root of 1 half less than or equal to 3 halves? This is 1.5. This is root 2 over 2, which is like 0.7. So yes, that is true. 0.7 is less than 1.5. So we're in region B. And we were doing dx earlier, and now we want to switch to dy on the inside and dx on the outside, which means dx on the outside, the outer integral is dx. It looks like dx is going from 0 to 2. And our dy, we start off at y equals 0, and it's going up to y equals x squared. And I guess I don't need to write the y part. And we've got our f of x, y on the inside. I gave myself too much space. I'm going to move that dy dx over. We've got our e to the x cubed now. Does this help us? I don't know yet, but we are integrating with respect to y first, and e to the x cubed is a constant with respect to y, which means doing the inner integral, we've got 0 to 2, and we've got dx, and it's going to be e to the x cubed times y, evaluated from y equals 0 to y equals x squared. And that's going to be e to the x cubed times x squared minus 0, which is just x squared e to the x cubed. And then we still have our dx. So let's finish making a note here. We sketched it based off the limits of integration, and then we found new upper and lower limits. Notice they are different. We did not have 0 to 2 or 0 to x squared in the previous setup. But now we have that x squared we wanted. We have the x squared dx, which means that should equal that. So let's make that substitution in. The only other part I'm going to add is let's change our limits of integration. So when x equals 0, u equals 0 cubed, which is 0. And when x equals 2, u equals 2 cubed, which is 8. And I'm deliberately putting the du here so that people can see where it came from. This is the 1/3 du up there. No, I'm not going to leave it like that because, yes, it's making me twitch too. I'm going to put the 1/3 out front. It doesn't have to go out front, but it shouldn't be after that. We should put coefficients in front of variables at least. If you skip moving that out to the front and just go straight to the next step where you actually integrate it, fine. And if you get hasty and just say this is 1/3 e to the 8, I'm going to have fun docking you points. Because e to the 0 is not 1, or not 0. Not too bad, right? So here you just had to like map it out, see what it looks like. Remember that the function doesn't affect your boundaries. Let's make a reminder of that. Reminder that f of x, y does not affect boundaries if you remap it. Is that always the case? Yeah. Were you, Chris? It smells like fresh baked chocolate chip cookies. Use double integration to find the area between y equals sine x and y equals cosine x. Well, if we map y equals sine, and they only give us one limit here. But let's take a look at what's going on pictorially. So that is like cosine x. And that is like sine x. And they're saying going from 0 to pi over 4. Where does pi over 4 go right here? It happens to be where they intersect, which is convenient. Yeah, sine of pi of 4 equals cosine of pi over 4, which is root 2 over 2, which is less than 1, of course, because they both cap at 1. So that's at like root 2 over 2 for the y value there. And we are looking for what's between sine of x and cosine of x and between 0 and pi over 4. So our 0 line is right here. And our pi over 4 line is right there, which means we want this region in here. That's not a very good cosine x. It should start out flat. It looks like it's going up a little bit, but I think you get what I'm selling. It should have a pi over for cosine. It should be pi over 4. You know, pi halves. What? Sine pi over 4 is equal to cosine pi over 4. Oh, I see what you're talking about. Yeah, I fucking wrote. That's because fucking Brian up here said root 2 over 2 right as I was writing pi over 4, and I heard the 2 and wrote 2. And I know that's what it is. We all make these mistakes. You start working ahead. All right, so that like doing area normally here, how do we learn this shit in Calc 2? You had an upper function minus lower function. This is like a to b f of 2x minus f of 1x dx. That was like how we did it in Calc 2. It's like one of the first things you did in Calc 2. But like this says use double integration, which means I'm going from an area to adding another dimension. Let's say it was a box, a square, and we add another dimension. We now have this shit going on. So that looks like we're looking at a volume. So let's say, like pictured here, let's use length and width and height. Volume is length times width times height, and area is just length times width. How can I work with volume and still end up with area? What has to be true? When does volume equal area? When one of the dimensions equals 1. And in this case, it looks like H, which is our Z component. Like if we called this XYZ, so, and Z is our f of XY. So what we're going to do, our f of XY is going to equal 1. That all leads to this statement right here. All right, let's look at doing the two setups here. Fuck. So if I do dy on the outside, I have one region, I got like a region 1 doing this, and region 2 is doing this. I'm going to have two different limits of integration. The left side is the same for both. We've got 0 is less than, what is that, x less than cosine x for the R2 region. We have 0 is less than x, which is less than sine x for the R1 region, the lower region. So, like, that doesn't look appealing to me at all. Is the other way any fucking better? We go that way, dx on the outside. It means we are going upward.
When it, like before, when we do it that way and we would split it into two integrals, does that mean that we'd have to do like two double integrals?
Yeah, we would have two double integrals here, which sometimes is the only route you got. Like sometimes doing the double integral, like imagine real quickly, if I scroll up, imagine the limits up here force us to do two integrals based on the boundary conditions when we do dy on the inside. We can't do dx on the inside. So if switching to dy makes us do fucking two double integrals or fucking 8 double integrals, either way, it's fucking doable at that point, whereas like the dx on the inside's not. So sometimes you have to switch. But if you don't have to switch, don't fucking switch. Go with the easiest setup. And so here we're going to have like the lower line is sine x, which is less than or equal to y, which is less than or equal to the upper line is cosine x. And it looks like x is between 0 and pi over 4, which was given to us. So let's do that. Let's do dx on the outside. And then my f of xy we said was 1. And then we have a dy and then a dx. All right, we integrate on the inside. I have y from sine x to cosine x dx, which gets us 0 to pi over 4 cosine x minus sine x dx. Which, if you notice, this is the same as that. which is good. It is showing us we are getting the area. And you might be like, well, why the fuck would we do the volume when the area was quicker? Sometimes doing the volume is the way that like it falls out. It's easier to switch to doing volume. Because by doing like here, the limits were nice and easy. But like when the limits are fucked and you try to do a specific order, the limits of integration might make it impossible to fucking evaluate the shit. But if we can switch to a double integral and then switch the order and use the easy method or the easier limits, then it falls out better. The integral of cosine x is sine x, and the integral of negative sine x is positive cosine x. So I have sine of pi over 4 plus cosine of pi over 4 minus sine of 0 plus cosine of 0. I end up with root 2 minus 1. Is that a positive area? Is root 2 minus 1 greater than 0?
1.43.
Yeah. So our area is positive, so that's a good sign. All right, integrate over the region bounded by y equals square root of x. Some fucked up line. Let's see. Throw some values in here. It helps to be precise when you're mapping this shit out because finding the points of intersection gets a little bit easier. Square root of x does this. Negative 1/2 x plus 3 halves means start at 3 halves, or 1.5. And then negative 1/2 means go right 1, down 1/2. Or you could say right 2, down 1, but in this case, doing right 1 and down 1/2 shows me I get the actual same point I had before. And it shows me where I intersect stuff pretty easy. So this is that line that we had. And then we had one more line. It said y equals 0. It is important. It gives us the lower limit, or it gives us an actual region to combine. Which means the region we want will be the region in green. Now, to find that point of intersection, we can set these equal. And if we square them, in the interest of saving time, we only got 6 minutes left. In the interest of saving time, this is going to fall out where you see that x does equal 1 and y equals the square root of 1, which is 1, which tells us that point of intersection is 1, 1. I felt pretty comfortable doing it graphically. I could see that they hit the same spot, but you should really do the algebra and make sure, unless you're 100% fucking confident. So now we got two possibilities. If we do dx on the outside, which is what I've been loving to do, that means I've got two regions, right? Without even looking at what they are, I'm like, I already don't like that. So let's like look at the dy outside. And that has us going from the red line up to the blue line. But it needs to be in terms of x. Because you can't have dy and have y in the limits of integration. That doesn't make no sense. So the red line, if I solve for x, I get x equals y squared. And that looks like my lower limit. It's the one on the left. My blue line is negative 1/2 x plus 3/2 equals y. And I want to solve for x. I think it's easiest to multiply by 2 on both sides first. And we get negative x plus 3 equals 2y. If I add x to both sides and subtract 2y from both sides, I get 3 minus 2y equals x. And that'll be my upper limit. This is nice. Neither of these has a square root in them. So we said let's opt for the dy on the outside. Dy on the outside means what is y doing? Y is doing 0 to 1. Yeah. And then my inside, we just got done talking about it. The lower limit was the red line, which is y squared. And the upper limit was 3 minus 2y. And we had f of x, y. I'm just going to make sure I put that in real quick. And when we upgrade to putting the shit in, it's just xy. All right, now it's straightforward. We focus on the inner integral. We're integrating with respect to x. That is going to give me a 1/2 x squared y evaluated from y squared to 3 minus 2y. And then I got my dx. I'm not going to rush this. I can put the 1/2 y on the outside. And when I do x squared, I have 3 minus 2y squared minus y squared squared. Do a little bit of sidebar bar here. 3 minus 2y, 3 minus 2y, 9 minus 6y minus 6y plus 4y squared. That is 9 minus 12y plus 4y squared. And that is y to the fourth. Which is not actually what we want to integrate. We want to multiply that y in. We can move the 1/2 to the outside, which is helpful. But we are integrating 9y minus 12y squared plus 4y cubed minus y to the fifth. That should be a dy on the outside. I wrote fucking, I was writing dx. Straightforward finish. We have 9/2 y squared minus 4y cubed plus y to the fourth minus 1/5 y to the fifth, evaluated from y equals 0 to y equals 1. No, yeah, 1/5. No, what's 1/6? Should have gone up to 1/6. I was looking at the wrong thing. That goes to 1/6. Y to the sixth, which makes that a 6. All right, I don't want to get a calculator, so I'm just going to get a common denominator. This will be 27 over 6. This is 24 over 6, 6 over 6, and 1 over 6. 27 minus 24 is 3, plus 6 is 9, minus 1 is 8. I end up with 4 over 6, which is 2/3. And that's a wrap for today. Tomorrow we're doing 14.3. It's worth looking at. We are looking at polar coordinates, which is something you presumably did in Calc 2 at the end. We did some, like, yeah, we're going back to that fun shit.
X equals R.
The polar coordinate like section is my least favorite section in all of fucking chapter 14. Because like the graphing that shit, like I don't remember what cosine 2 theta fucking maps out to look like. I don't remember what these like the roses and the fucking the heart, the cardioids, and I know there's weird names for shit, but like I don't remember how they map out.
There's the
Yeah,
like the petals and then it's like
the petals seem to be easier, like than doing the cardioid. At least when you're mapping it out, like the mapping it out is straightforward on those.
Spent like at least 2 full days of just like focusing on it because I was like, okay, this is how you place it, and this is how you graph it.
Right.
And I was losing my mind.
Fun section.
Very fun.
All right, let me hit stop record.
Because didn't we have on the final two? Or yeah.